Hello everyone, this is the first lecture for the MOOC course on SWAYAM on analog electronic circuits, and this course is meant for undergraduate students maybe in their second or third year. And let me first start off by discussing the contents of the course. So, the content of the course, the primary content of the course is to learn about amplifiers, and as part of this endeavor we are going to start with basic nonlinear circuits. Including circuits that involve the use of diodes. Then we are going to start using Mosfets. So, with MOS devices we are going to first make very basic amplifiers, single transistor amplifiers, common gate, common source, common drain amplifiers. Then we are going to start making 2 transistor multi transistor amplifiers. Okay. Then we are going to study differential circuits, followed by the effect of capacitance. So, the performance of these circuits with frequency. Then finally, we are going to work on the op amp, that is we are going to learn how to design an operational amplifier. This course will also try to cover a little more specialized topics like power amplifiers, voltage regulators, and if time permits, oscillators. So, this is a very brief outline of the content of this course, and to start with in today's lecture what we are going to discuss is what are amplifiers and what is the meaning of our course title. So, this is going to be my objective number 1. Okay. So, to start with, the title of the course is Analog Electronic Circuits. Now, you have all heard about digital circuits, and analog circuits are the antonym of digital circuits. Now, the natural question is, if the world is going digital, why should we study analog circuits at all? And the answer for that is that indeed the world is going digital, but our world, the world around us, is all analog. So, to give you an idea, the picture that you see is analog. Okay. When you see something, it is analog. When you hear something, it is an analog perception. When you smell something, it is an analog perception. All of our perceptions are analog, but when it comes to sending information to a computer for further processing, you would like to send it as in a digital format. So, in between there has to be a circuit in between this analog world of ours and the digital computer. There has to be a circuit in between that converts the analog stuff, takes it, senses it, amplifies it and converts it into digital, and then hands it over to the digital circuitry that processes, right. So, this is This is the basic idea. So, the difference between analog and digital, according to me, the easiest example is that of a thermometer. So, if you think of a mercury thermometer, so this is your standard mercury thermometer, and on the side you have these graduation marks, right, and if the column of mercury reaches a certain height, then you read out what the temperature is. So, the column of mercury reaches a certain height and you read out that, oh, the temperature is whatever is written over here, 102.4 degrees, suppose. Okay. So, this is an analog system. A digital system would not have this column of mercury. Instead, a digital thermometer is just going to say, oh, the temperature is 102.4 degrees, and it would be written digitally on the thermometer itself. So, the difference between analog and digital is that a digital system is discrete. It can do 102.4, can do 102.3, 102.2, 102.1, 102. It can't do 102.25. Whereas, in an analog system, this could have been slightly more, and it is up to you to make that reading. If you can read it as 102.25, then great. If you can't, it is your problem, right. So, an analog system naturally has precision, whereas the digital system is imprecise, right, it is discrete values. Okay. So, this is the basic difference. The digital system is going to give you this reading. The same thermometer, digital thermometer will read you 102, an analog thermometer you will have to read according to the column of mercury. Okay. So, everything around us is an analog perception, whereas the computer is digital, which means that every photograph has to be digitized and then processed. Okay. So, in a typical system, what do we have? In a typical system, we are first going to have a sensor. So, let us think of a photograph. So, a photograph will first have a sensor. To take a photograph and digitize it, first you have to have a sensor. This sensor is an array of pixels in case of a photograph, right, lots and lots of pixels. All these pixels are going to produce voltages which are proportional or which depend on the amount of light that has fallen on them. So, this sensor is going to produce a voltage. So, I am saying a voltage, but in case of an array of pixels, it is a set of voltages, right. And what is the first thing that you have to do? The first thing that you have to do is to make sure that the amount of noise in the system does not corrupt what has been sensed. Okay. And to do that, you first have to amplify this. You have to first increase the value of the voltage, so that in such a way that the noise in the system does not corrupt the individual voltages. Okay. And for that reason, we are going to use an amplifier. Okay. And then what are you going to do? Then you are going to use an analog to digital converter, and then you are going to take the digital samples and store it in memory or do whatever else that you want to do. Okay. Another example is voice. Okay. Suppose I am talking, okay, not through the internet, I am just talking in a class, and there is a microphone over here. So, my speech is going straight to this microphone. Then the microphone converts this speech into a digital signal. So, this microphone is catching the speech from my voice, right. And what does it do? Inside the microphone there is the carbon is packed in, and according to the sound pressure level the resistance of the microphone changes, right, and that is your pickup. Okay. So, eventually what happens is that if I push a constant current through the microphone, then the resistance is changing, that creates a voltage, right. So, the voltage changes. Okay. So, this voltage has to be sensed. So, you have got my speech, then the speech goes to the microphone effectively is going to produce a voltage, right. This voltage goes through this long wire, and in my pocket there is this battery operated amplifier, right. This battery operated amplifier is going to convert this voltage. First it is going to amplify it, then it is going to digitize it, then it is going to convert it into an RF signal, right, and over the radio frequencies it is going to communicate to the sound system that is far away, okay, but that is a digital signal. So, this is the general idea. This amplifier happens to be a basic building block. Okay. Why is this amplifier the basic building block? Because right after the sensor you always need that amplifier, you cannot not have that amplifier over there. Okay. In fact, what happens is that there is one amplifier, and then there is a reasonable amount of signal processing in between the amplifier and the A to D converter. Then the A to D converter converts it to digital, and finally there is a large amount of signal processing in the digital domain. But it is much more economical to have a significant amount of signal processing in between the amplifier and the A to D converter, and that is also an analog circuit. Okay. So, this is the analog world. And in the analog world, one of the most basic building blocks is the amplifier. All right, one more example. Classic example is the hard drive of a computer. So, the hard drive of a computer, there is a platter, let me draw it. I do not know if you have seen the insides of a hard drive, but this platter, I mean if you think of a 1 terabyte hard drive, it has one kilo means 1000, mega is a million, giga is a billion, tera is a trillion, right. So, 1 terabyte refers to 1 trillion bytes. So, 1 trillion bytes, 1 into 10 power 12 bytes, and each byte is made up of 8 bits. This is stuff that you know already. So, there are actually 8 into 10 power 12 bits. Now, on a magnetic hard drive, these bits are stored as little magnets that either point to the north or they point to the south. All right, is that understood? So, these 8 into 10 power 12, that is a gigantic number. So many little magnets have been organized into tracks, right. They have been organized into tracks around the spindle of this platter, right, and each magnet is tiny, it is a tiny particle, and that particle is residing, it is either pointing this way or it is pointing the other way depending on whether it is a 1 or a 0. Okay. So, all of these are on these tracks. Now, this hard disk is spinning around at an incredible speed, right. So, this is going round and round at, let us say 5400 rpm. How many revolutions is that per second? Okay. So, rpm is revolutions per minute. Think about it, it is spinning 90 times per second. Okay. That is incredibly fast, it is spinning, right. And you have to read from this while it is spinning. So, what is done is there is a magnetic head, and that magnetic head comes and flies on top of this platter, very close to the platter. It flies at the right place, flies in on the right track, right. Suppose it has to read a certain file, you have to read this JPG file from the hard drive, you have to access it. So, the computer knows where on which track this JPG file is. So, it sends this read head. So, this is the read head. Okay, this is your platter. So, the read head has to align itself to the correct track or the correct cylinder in the words of the hard drive, this is called a cylinder. So, it goes to the right cylinder, right, correct track, and then sits, it flies right on top, because it has to fly. Why does it have to fly? Because if it touches the spindle and the spindle is revolving at an incredibly fast speed, you are going to get a scratch on the spindle and there goes everything. So, it can't touch, it has to fly very close to the spindle, maybe a micron above the spindle, right, and it has to sense all of these magnets that are going underneath it, the orientation of all of them. Okay. So, invariably if you look at the voltage coming out of this, right, it does not really look like, I mean you would want it to look like a series of ones and zeros, right. You think it would look like this, it does not look like this at all. In fact, it has no resemblance to ones and zeros at all, it probably looks like some noisy signal. Okay. And this signal has to be amplified, then you have to do a significant amount of signal processing to work out exactly what those bits were that were on the platter, that were residing on the platter. So, each bit is actually interfering with the next bit. So, when you think you are reading one bit, you are not really reading one bit, you are reading 10 bits or you are reading many bits at the same time. So, each voltage sample over here is the effect of many different bits. So, if you think about it, it is not something very straightforward, and digitizing this signal makes no sense at all. Okay. So, you have to do a large amount of analog signal processing with this particular voltage to obtain, finally you want to obtain this digital signal, but what you get is this, right. You have to do an incredibly large amount of analog signal processing to arrive at this from this. Okay. So, this is just to give you an idea of the importance of analog circuits and the flavors of analog circuits that we are going to talk about. We might not be talking about this kind of analog circuit in this course, but I am just trying to point out that these are examples of classic analog circuits. Okay. Next, we are going to start with the amplifier. Now, when I talk about an amplifier, what does it amplify? For example, I mean I want to illustrate the question, let us see if you understand the question. Think of a transformer. Suppose this transformer has a turns ratio of 1:n. Okay. I apply a voltage V naught cos omega t on the primary side. On the secondary side, the voltage I will get is n times V naught cos omega t. Is this transformer an amplifier? Is it an amplifier? Is the transformer an amplifier? Do you think it is amplifying anything? Is it? Well, the voltage is increasing. I mean V naught cos omega t on the primary side, on the secondary side you had n times V naught cos omega t. The voltage is increasing, but what about the current? At the same time, if I had some current I over here, the current on the secondary side would be I by n, right. So, if I had on the primary side, if my current was I, on the secondary side my current is I divided by n, which means that effectively if I increase the voltage n times, the current is decreasing n times. That is happening because power is being conserved, right, energy is being conserved, there is no loss in this ideal transformer. Okay. Great. So, whatever power you are throwing into the transformer is coming out of the transformer. Okay. So, in this case we say that the transformer does not amplify anything, this is not an amplifier. Okay. The transformer does not amplify anything. Why? Because whatever power you throw at the transformer at the input, it comes out at the output. If at all, the output power will be less than the input power, it will not be more than the input power. All right. So, the transformer does not amplify anything, even though the voltage on the secondary side increases, right, it does not amplify anything, the transformer is passive. Okay. So, what does an amplifier amplify? Now, I come back to the question. Now that I have illustrated why I am asking the question, I come back to the question. When we are going to talk about an amplifier, what do we need to amplify? The voltage? No, because a transformer can also increase the voltage, right. A transformer is not an amplifier. Okay. So, not voltage. Current? No, right, because a transformer could also have increased the current, you just switch the primary and the secondary. You call the n side as the primary and the one side as the secondary and you are done, right. You can increase the current at the cost of decreasing the voltage and it is still passive. So, it does not increase the voltage. An amplifier is not just something that increases the voltage, an amplifier is not just something that can increase the current, because these can be achieved with a transformer too. An amplifier will amplify power. So, the answer to this question is power. Okay. When I say amplify what? You have to amplify power, an amplifier has to amplify power, all right. And then you are going to say that you have learnt a lot of physics and you know class 11, class 12 and so on and so forth, and the law of conservation of energy is the guiding principle of the universe and there is no way to violate the law of conservation of energy. So, what is this gentleman talking about? I mean, he is saying that an amplifier is something that amplifies power. This cannot be right, because nothing, there is no way to amplify power. You can't, I mean, if you have a system and I throw some power at it, then you can't get more power out of it. Okay, there is no way that it will produce more power than it was given, right, because you have to also follow the law of conservation of energy. I agree, you have to follow the law of conservation of energy, there is no way out. So, what we normally think of is a black box. Think of a black box, and in this black box I am willing to give you extra power from a battery. Okay, this is a battery. Take as much power as you want from the battery. Now, I am going to give you an input. So, here I am showing a sinusoidal voltage source, but this is really a sensor, right. And when we say that it is a sensor, the sensor is going to have some source resistance, because if it does not have a source resistance, then you can use that voltage source directly and it will produce whatever power that you ask it to produce. Whereas, if you have a source resistance associated with the sensor, then the amount of power that that particular voltage source can produce is limited. Am I right? What am I talking about? So, if you have a voltage source with, let us say, V naught cos omega t is the voltage source, and let us say this is R s is the source resistance, then what is the maximum power that can be generated, that can be produced by this voltage source? So, the maximum power is drawn by a load. This is the maximum power transfer theorem. You know, this is recapitulation, right. So, maximum power is drawn by R L when R L is equal to R s. If R L is equal to R s, then the current is V naught cos omega t by 2 times R s, and therefore, the power in R L is going to be square of that times R L, and then you have to take the RMS, which gives you a by root 2. Okay. So, the maximum available power. So, what is the power in R L finally? V naught cos omega t by 2 is the voltage across R L. Okay. So, if I just take the amplitude, right, I do not want to keep writing cos omega t then cos omega t squared, I can do RMS, right. Let me just do phasor and RMS and so on. So, the phasor for this is going to be V naught by root 2. Okay. So, the phasor voltage across R L is going to be V naught by 2 root 2. Okay. And the phasor current is going to be V naught by root 2 by another V naught by root 2 and then 2 R s. So, V naught by 2 root 2 times R s is the phasor current, and effectively that gives me V naught squared by 8 R s, where V naught is the amplitude. If V naught had been the RMS already, okay. So, if your amplitude is V naught, then the maximum power in RL is V naught squared by 8 R s. So, this is also called the available power. Okay. So, the available power in that sensor is limited. When I say that the available power is limited, then that means that this R s is some finite value, because if R s had been equal to 0, then the maximum available power can be infinite. You can get whatever power you want out of that. Okay. So, that is what I wanted to point out, and it all comes from the maximum power transfer theorem. All right. So, this is my setup. My setup is that I have a sensor which comprises of a voltage source in series with a source resistance, and this is going to go to a black box. This sensed voltage is going to go to a black box. This black box is going to be powered externally with a battery, and you are allowed to draw whatever power you want from the battery. Now, the black box is going to output voltage onto a load, or it is going to output power onto a load, right. This load need not have anything to do with R s now. Okay. These two are now unrelated, right. If this black box had not been there, then maximum power would have been transferred if R L would be equal to R s, but right now they are not related at all, okay, because I have put a black box in between. Now, the question is that this available power at the input. So, the maximum power that I can draw from the input, this black box can draw a maximum of V naught squared by 8 R s over here. That is the absolute maximum power that this black box can draw from the sensor. But with the help of the battery, can I produce any arbitrary power and drive it onto the load? Okay. If I can, then this is called an amplifier. Okay. It is amplifying power. Okay. At the end of the day, it is amplifying nothing. I mean, there is no amplification. At the end of, I mean, power is conserved. At the end of the day, it is drawing power from the source, it is drawing power from the battery, and it is throwing power out into R L, and it is also going to heat up on its own. So, you have to have the law of conservation of energy with all of these things. It is drawing power from the source, it is drawing power from the battery, it is throwing power out onto the load, and it is having self heating. Okay. So, you do the law of conservation over here at the end of the day. Okay. So, it is not really amplifying power as such. However, if you look at the signal is coming from the sensor, right. I want a scaled version of the signal. So, if this is V in, I want a scaled version of the signal k times V in over here, not a constant voltage. Okay. Some, I mean, k can be positive, negative, large, small, whatever you want. Okay. K is some value. So, this is the relationship of the amplifier, and at the end of the day it would have therefore amplified power. I mean, k squared by sorry, this is amplifying voltage by a factor k, right, but the current is not really going down in this case, right. The current over here is k V in by R L, that is the output current. The voltage is k V in, right, which means that the output power is k squared V in by R L. Okay. The maximum available power was something else, something related to R S. R S and R L are unrelated, R S can be very large, it does not matter. So, even though power was not really available from the source, with the help of the battery you would have provided power to the load such that input output relationship is maintained. Okay. So, that is the entire idea of the amplifier. Is that clear? Okay. Now, to make such an amplifier, will you be able to make it with passive elements? This is how many ports are there in this? 1, 2, 3 ports, right. Is it okay if I would you be able to make a 3 port network with passive circuit elements, right, basically resistors, inductors, capacitors, do whatever you want. Will you be able to make this circuit? Is it possible? Yes? No? Okay. Yes, you cannot make such a circuit with passive elements using resistors, inductors and capacitors. It is not possible to make this amplifier. Why not? Why not? Because the battery is going to produce power, it is going to produce power at DC. Okay. So, if this circuit is passive, then DC power will remain DC at the output. It is not going to be translated to the frequency of the input voltage. The input might be at some other frequency, right, it might be at some frequency omega. I want the DC power to be translated to frequency omega. Okay. And linear circuit elements do not allow such things to happen. So, think about it, I gave you the answer, but think about it. Okay. It might the answer is I gave you a compact answer, but think about it, you might not understand it in the first shot, rewind, ask yourself again, take clues, take hints from what I just said, that the DC power is never going to be translated into any other frequency. Suppose the frequency is at omega, right, omega power is going to be fine, it is going to remain at omega if the circuit is linear, right. We are talking about linear passive elements like L, C and R. As long as the circuit is linear and passive, input power, input frequency will get is fine, will remain, you will get the same power or less at the output, and whatever power is being produced by battery will remain at DC. Okay. So, think about my answer, rewind, rework this a few times before you convince yourself that this amplifier cannot be made at all using components like L, C and R only. All right. So, what do you need? As I said, you cannot use L, C and R only. What do you need? Can you use other passive components? Can you make this amplifier with the help of diodes? Can you? The answer is no once again. So, as long as you have passive components, you can't do it. Okay? Not just linear. This box has to be made using active components. It is not sufficient to have only pure passive elements in this box. Okay? You need to prove this to yourself, think about it. Okay. So, can you fill up this table? Linear passive components are what? R, L, C, transformer, mutual inductance, right, these are all linear and passive. Transmission line, yeah, these are all linear and passive elements. Okay. Nonlinear passive elements, give me an example. Diode, great. Active, linear active elements, do you know of any elements that are linear and active? Example, voltage source, okay, current source. These are two main things, right, voltage source and current source, and you have the controlled sources. So, you have CC, CS, CC, VS, voltage controlled voltage source and voltage controlled current source. Okay. Now, of course, these 5 elements we do not really know how to make them, right. You might know how to make a voltage source, right, you can make a battery, you can buy it in the market, battery is a voltage source, but current source we do not yet know how to make current sources, and all these controlled circuit elements are all they have been discussed in your circuit theory class, in other network theory classes and so on. However, I am sure right now you have no idea how these components can be made. Okay. So, we will have to live with only the voltage source as a linear active element. Okay. Then come the nonlinear active elements. Any ideas? Any names that you have? Any names that you have for the nonlinear active elements? Okay. The Mosfet, and that is going to be a primary subject matter of this course, the Mosfet, how it behaves. Okay. And like the Mosfet, there is another transistor called the bipolar junction transistor. And then again there are other lots of other different kinds of transistors. There are JFETs, there are all kinds of other MESFETs, right, all kinds of other devices exist, and all of these are non-linear but active devices. Okay, great. What about the LED, the light emitting diode, what is it? Active, passive? Okay. So, it is a diode. Okay. Light emitting diode is non-linear, but it is a passive element, it is just a diode. Alright. So, this covers the spectrum of non-linear, linear components, and going back to this discussion of the amplifier, right. If you had linear circuit elements, frequency would be conserved in terms of power, which means that the amplifier cannot be made with only linear elements, it has to have non-linear elements. Okay. So, you need non-linear and at the same time you need active circuit elements. So, we have to work with devices in this last bracket, right. In particular in this course we are going to work with the Mosfet. The BJT used to be used to be the subject matter of this course. However, the BJT has been phased out. The BJT has been phased out of almost all analog circuits except maybe 1 or 2. So, my feeling is that you can study the BJT by yourself if required. In general, it is not going to be required. Is this okay? Can we move on? Okay. So, the first circuit element that we are going to study in this course is the diode. And we will start from the symbol of the diode. Okay. So, diode is made out of a p-n junction, all of that is there, we are not going to bother about it. However, if the current through a diode is I and the voltage across it is V, then V and I have a certain graph. What does that graph look like? Do you know? I am sure you know that. Yeah. So, an ideal diode, a diode that I would really like to purchase, but is not available in the market, would have a characteristics that looks like this red curve, or you can't really see it because it is merging with the axis. So, it is going along the negative x axis and the positive y axis. That is, when V is negative, I want 0 current, and when V is positive, I want infinite current. That is, when positive V cannot exist because the current through that becomes infinite. So, current can go only in one direction, and when the current goes in the forward direction, then the voltage across the diode is 0. This is the one diode that I would like to purchase from the market. Unfortunately, the device manufacturers are unable to give me this device. In fact, they just can't make it. In fact, they have gone so far as to claim that this particular device cannot be made by anybody, right, and they are never ever going to be able to make such a device. Instead, the device that they are going to give us has some non-idealities, some small imperfections. Okay. So, what are those imperfections? Number one imperfection is that it does not it starts conducting not at 0, but at a voltage close to 0. So, there is a non-zero knee voltage over here, non-zero cut in voltage. So, this is called the cut in voltage, let us call it V cut. Okay. So, in which case the model for the diode would have looked like that. So, it would merge with the x axis as long as voltages were below Vc, and above Vc you cannot apply a voltage because any the current would become infinite, right. So, it would be on, it would not have any drop above Vc. Okay. So, this is the first level of abstraction. Then they say, the device manufacturers say that no, they can't give me this either. They are going to do one more round of abstraction, right, and they are going to, the next level of abstraction is something that rises above Vc, but not vertically. okay, it rises smoothly, all right. And then the device manufacturers further go and say that no, even this is not possible. What they are really going to give is something that also falls a little bit. So, my figure over here is exaggerated, the little bit that I have shown is actually much smaller, it falls a little bit, okay, below the x axis. Okay. In fact, there were a few device manufacturers who said that let us try making this perfect and so on and so forth. Then the circuit theory guy came and said that no, you can't do it, you have to pass through the origin. Okay. So, I will come to that. So, the first level of abstraction, the red curve, is what? The red curve can be mathematically expressed as I equal to 0 when V is less than 0 and V equal to 0 when I is more than 0. So, this is the first graph, the first abstraction. This is what I wanted to buy, this is the ideal diode. The next level of abstraction is that no, I can't do V equal to 0, I will do V equal to Vc when I is greater than 0, but for V less than Vc I will be equal to 0. Okay. So, this is the second one. And then the third one, what is the third one? The third one says, I mean the device manufacturer finally says that no, I can't make all of these things, this is all discontinuous and so on, whatever I make it is going to be some continuous function, and he says that I will give you I equal to some constant, some scaling constant times some exponential of V by Vt. Here Vt is Kt by Q. Okay. So, this is what the device manufacturer wanted to give. Then came the circuit theory expert. He said that no, you can't make this, it is not possible to make this, you have to make, you can attempt to make this. Why is that? Why did the circuit theory man say this, not the device expert? This extra -1 had nothing to do with the device expert. The device expert could not really measure that -1, right. E power V by Vt was so large that he could not measure the -1. The circuit theory expert came and said that there has to be a -1 over there, otherwise you are doing something wrong. Why? Why does it have to be there? I mean, we are in a circuits class, so we understand circuit theory, that is the assumption. Why does the -1 have to be there? Because at V equal to 0, I has to be equal to 0. If it is not equal to 0, then the device can produce, the device can generate power, and this is a passive device. Okay. So, that is why that -1 has to be there by I mean you have to put that -1 if you want to work close to V equal to 0. Okay. So, this is these are the abstractions of the diode. Let us stop here, and in this class all the first we discussed the basic course outline, right, very briefly we discussed the basic course outline. and then we discussed different examples of analog circuits, the thermometer, right, and how the amplifier is a basic building block. Some analog signal processing was discussed with the hard disk platter. Then we started working with the big question, amplify what, and the answer to that is power. The transformer is a passive device, it does not amplify. Then we discussed a strategy to actually amplify power. You are not really amplifying, you are not really violating the law of conservation of energy, you are supplying power from a battery and supplementing, but effectively you are amplifying power between V in and the output. Okay. We discussed passive devices, active devices, and the amplifier has to be made with nonlinear and active components. And finally, we started our work with the diode, right. We discussed different models of the diode, and in the next class we are going to work with diode circuits. Thank you.